This is your lecture on general senses, and hopefully you have your notes. We'll just follow your notes as we go through this. I'll be reading through my notes that I gave you. So we have sensory receptors, or specialized cells, that provide the central nervous system with information about conditions inside or outside the body. The translation of a stimulus into an action potential is called transduction. Okay, a particular type of a stimulus like light or vision. You have free dendrites in your skin for pain, for pressure, that type of stuff. Temperature, those are different types of reception. The general senses: pain, temperature, touch, pressure, vibration, and proprioception. Proprioception is like balance, equilibrium. Special senses: you have smell, which we call that olfaction. Remember, cranial nerve number 1 is the olfactory nerve. Taste, gustation. Gusto means taste. Balance is equilibrium. Hearing, and sight, which is vision. Each receptor has a characteristic sensitivity. This is called receptor specificity. What does this mean? That means that the receptors are specific for monitoring or picking up a particular type of stimulus, such as, the rods and cones for vision, the receptors in your skin, like your Pacinian corpuscles, for pressure. You have free nerve endings for temperature and pain. So you have different types of receptors. Baroreceptors, which are pressure receptors, like in your blood vessels, for measuring blood pressure and controlling your rate of respiration and the rate of your heartbeat. The simplest receptors are free dendrites of sensory neurons. Some of these respond to tissue damage as a result of chemical stimulation, pressure from swelling of the tissues from fluid collection, temperature changes due to increased blood flow, and trauma to the tissue like a bruise or damaged tissue. More complex receptors, such as rods and cones of the retina, that's in your eye, are protected by accessory cells and layers of connective tissue. There's several layers of cells to make up your retina, and the rods and cones are the deepest. The receptive field is the area being monitored by the receptor, the area that's being monitored. The fewer the number of receptors being affected by a stimulus, the greater the ability to localize a stimulus and vice versa. When sensory information arrives in the central nervous system, that's the brain and spinal cord, it's routed according to the location and nature of the stimulus. Touch, pressure, pain, temperature, and taste sensations arrive at the primary sensory cortex and the parietal lobe. Visual sensations arrive in the visual cortex, which is the occipital lobe, and auditory and olfactory sensations arrive at their respective regions of the cortex and the temporal lobe on the side. The neural link between the receptor and the cortical region is called a labeled line. The central nervous system interprets sensory information entirely on the basis of the line over which it arrives. The identity of the active labeled line indicates the location and nature of the stimulus. All other information, called sensory coding, provides information about the strength, duration, variation, and movement of the stimulus. The coding is like if someone grabs your arm, you know that they have you, but if they squeeze, it's a more forceful grab, and so the pressure receptors are registering more force. And that's an example like sensory coding. Or your eyes, when the light increases and increases and increases, brighter and brighter and brighter, it gets more and more painful. And the same thing with your ears. The sound gets louder and louder, that also gets more and more painful. That's sensory coding. Tonic receptors, T-O-N-I-C receptors, are always active. When the stimulus increases or decreases, their rate of action potential generation changes accordingly. So they're pretty much always active, always going to register a change in the environment, like your eyes will do that for sure. Phasic, PHASIC receptors are normally inactive. They become temporarily active when there's a change in the conditions they're monitoring. Okay, so this is how you adapt to things like a necklace. Now you feel it. The shoes on your feet. Now you feel it. You know, a ring on your finger, a watch on your wrist. You've adapted, or they've adapted, and when your attention is drawn to them, then you register it again. So they adapt to prolonged stimulation. Adaptation, ADAPTATION, is a reduction in the sensitivity of a receptor in the presence of a constant stimulus. So the phasic receptors will adapt relatively quickly. Peripheral adaptation, PERIPHERAL adaptation, occurs when the receptors of sensory neurons alter their levels of activity. In this situation, the receptors respond rapidly at first, and then their activity decreases. These receptors are also called fast-acting receptors, since the tonic receptors are always active and show little peripheral resistance. They are called slow-adapting receptors. Now we have something called central adaptation, CENTRAL, occurs within the central nervous system as a result of inhibition of sensory nuclei along the sensory pathways. Receptors can be divided into groups according to several schemes, and we have several of them here. The first blank is exteroceptors, EXTEROCEPTORS, provide information about the external environment. That's why they're called exteroceptors. The external, like smell, vision, hearing, taste, temperature, pain, those are external stimuli. The next blank is interoceptors, INTEROCEPTORS, or visceroceptors, monitor conditions inside the body, like pain, pressure, hunger, and thirst. Visceral means organ. Proprioceptors, PROPRIOCEPTORS, receive information concerning body position and movement. That's the equilibrium. A more specific classification would be according to the nature of the stimulus which excites the receptor. Next blank is nociceptors, NOCICEPTORS, detect pain due to temperature and physical or chemical damage to the tissues, like cutting, burning, swelling of some form. Number one there, myelinated type A fibers. If you remember, myelination of a fiber, like an axon or a dendrite, will increase the rate of conduction of an impulse. So myelinated type A fibers carry sensations of fast pain or prickling pain. An injection or a deep cut produces this type of pain, kind of like a stinging pain. Number two, unmyelinated type C fibers carry sensations of slow pain or burning and aching pain, like when you exercise. Endorphins and enkephalins are neuromodulators. NEUROMODULATORS, whose release inhibits activity along pain pathways in the brain. These compounds, similar to morphine, are found in the limbic system, hypothalamus, and reticular formation. Pain centers in these areas use the neuropeptide substance P as a neurotransmitter. Endorphins bind to the presynaptic membrane and prevent the release of substance P. thereby reducing the conscious perception of pain, although the painful stimulation remains. We have something that's a cynic type of it mimics endorphins. It's called morphine. Thermoreceptors. THERMORECEPTORS are free nerve endings which detect changes in temperature. That's why they're called thermoreceptors. They are found in the dermis of the skin, skeletal muscles, the liver, and the hypothalamus. They are phasic receptors. That means they can adapt. Just like when you step in a hot shower, it kind of hurts at first, and then it becomes okay. You adapt to it pretty quickly. Mechanoreceptors. MECHANORECEPTORS, mechanical things or physical things, detect physical stimuli which results from the physical distortion of a cell's membranes, like somebody squeezing on you. You know, the receptors for touch, and then you squeeze it and it's over distortion. It's painful. These membranes contain mechanically regulated ion channels whose gates open or close in response to stretching, compression, twisting, vibrations, or other distortions. Number 1, tactile receptors, TACTILE. Now, tactile means touch. It says monitor touch, pressure, and vibrations. Can be free nerve endings to specialized structures. Now, go ahead and read through these. There's an A, B, C, D. We'll pick up at E. Okay, so read through those. E, Pacinian corpuscles, and there's a new name for that. It's called lamellated, LAMELLATED corpuscles. Lamellated means layered, like layers. Corpuscles are composed of a single dendritic fiber surrounded by concentric cellular layers. It kind of looks like you've cut an onion. You see the layers of onion cells. They're scattered throughout the integument, as well as superficial and deep fascia, joint capsules, the mesenteries, and the wall of the urinary bladder. Now, the Ruffini, that's a person's name. They're type of a tactile disc, most sensitive to pulsing or high-frequency vibrating stimuli. Ruffinis are. So let's look at number 2, baroreceptors. BAROCEPTORS. Monitor changes in pressure in the walls of blood vessels. Barometric pressure, like your blood pressure 120/80. That's 120 millimeters of mercury over 80 millimeters of mercury pressure. Systolic over diastolic pressure. Aorta, carotid arteries, lungs, the vena cava, the digestive tract, urinary tract, and reproductive tracts. They are going to be monitoring or monitored by these baroreceptors. Proprioceptors, there it is again, PROPRIOCEPTORS, monitor body position and movement. This is like your balance. And I gave you some things in here, muscles, muscle spindles, and joints. They're a type of proprioreceptor too, as well as the Golgi tendon organs, which kind of relay information about how much stress you're applying to something with your muscles. Next blank, chemoreceptors, CHEMORECEPTORS, are receptors which respond to water-soluble and lipid-soluble substances dissolved in the surrounding fluids. They're the free endings of nociceptors, which may be stimulated by a variety of chemicals like oxygen, carbon dioxide, hydrogen ions for pH, acids, histamine, various enzymes, and prostaglandins. These receptors are found within the carotid bodies, CAROTID bodies of the internal carotid arteries. So those are coming right off of, your heart. The aortic bodies of the aortic arch, that's in the aorta, the large artery coming off of your heart, and in the respiratory and cardiovascular centers within the brain. The brain is real sensitive to pH, oxygen, glucose, very sensitive. So let's look at a slide. Let's look at our general senses PowerPoint. And the first slide there we go, olfactory. So olfaction, the sense of smell or olfaction. The receptors are located in the nasal cavity on either side of the nasal septum. If you remember, your nasal septum is right in the middle between your nostrils, and it goes inside the same way. The olfactory organ consists of, let me get my little finger there, here it is over here on the right, the olfactory epithelium. Now we're going to see a similarity in the arrangement of these senses, like the nose and the taste buds. So this olfactory epithelium and the gustatory epithelium are pretty similarly set up. So let's look at A, which is olfactory, O-L-F-A-C-T-O-R-Y. Bipolar neurons, and here they are, these little blue-gray cells here. These are bipolar neurons. And that's really all that olfactory nerve number 1 is. It's one cell layer thick of bipolar neurons. The distal end has up to 20 free dendrites, or they call them olfactory cilia, right there. You can see them here in the mucus, down at the bottom, which extend into the surface layers of mucus, where dissolved chemicals interact with receptors on the membrane surface. The cell body lies between the supporting cells. The axons of these bipolar neurons form cranial nerve number 1. So this end, this is the dendrite, and you have the olfactory hairs up in the mucus layer, which are going to receive the molecules for smell, that are given off by objects. The cell body of this neuron is right there. It's a bipolar neuron. And then the axons going up through the cribriform plate of the ethmoid bone up to synapse with the olfactory bulb. Olfactory nerve, it's number 1. These axons pass through the olfactory foramina of the cribriform plate of the ethmoid bone and synapse with neurons in the olfactory bulb. Axons leaving the olfactory bulb, which is up here, there it is. See, there's synapsing there, there's the bulb. Travel along the olfactory tract, this long structure here, to reach the olfactory cortex, that's in the temporal lobe, the hypothalamus, and portions of the limbic system. Remember, the sense of smell is the only sense that does not go up through the thalamus. All the other senses go up through the thalamus. B, so we had the olfactory cells, these little kind of blue-gray ones. Well, what hold them in place are these little pink ones here called supporting cells. S-U-P-P-O-R-T-I-N-G. Supporting cells. So they kind of fill the space in between the olfactory cells. It says columnar cells of the mucous membrane. Some of these columnar cells have differentiated into goblet cells. Remember, goblet cells make mucus. And that's going to be what these olfactory cilia are embedded in, is that mucus. The lamina propria, L-A-M-I-N-A, second word, P-R-O-P-R-I-A, lamina propria, a layer of loose connective tissue which holds the nasal epithelium, which is only one cell layer thick, to the bone, to the underlying bone. It also contains nerves and blood vessels, these little structures you see inside of there, nerves and blood vessels, which bring oxygen and nutrients to the epithelium and remove carbon dioxide and waste products. Okay, so lamina propria is like a glue zone that holds this olfactory epithelium to the underlying bone, the cribriform plate of the ethmoid bone. Now, There is another cell down here, which I didn't point out. The basal cells. C is basal cells, B-A-S-A-L cells, these right here. So cells probably produce new olfactory cells. Okay, they're called basal cells. Gustation, the sense of taste. Gusto means to taste, that's what it means. The receptors are located in taste buds located on the tongue, the soft palate, and the throat. You know, you've tasted things in the back of your mouth also that are not just on your tongue. When you swallow sinus drainage, there's a taste to that. When you get hot sauce way back in your throat, it's not on your tongue anymore, but you can taste it in the back of your throat. To taste something, the material must be in solution. It has to be dissolved in solution like water. Saliva is the fluid used to suspend or dissolve a food source so it may be tasted. Soften to swallow and begin carbohydrate digestion by way of amylase. It's called salivary amylase. So saliva will allow something to go into solution. It softens it because it makes it moist, and salivary amylase starts the carbohydrate metabolism. So digestion starts in your mouth. Let's look down here. We have a taste bud. And we have several papilla on the surface. But let's look at a taste bud down here and look at the profile of it. A is gustatory cells. There it is. Gustatory cells. Okay, those are the cells for taste, gustatory cells. It says 40 to 50 per taste bud. Each cell contains hair-like processes called microvilli or taste hairs, and there they are sticking out of the taste bud, the microvilli taste hairs. These cells are replaced about every 10 days, and that's true. If you go somewhere where they don't have sugar, let's say, and you're there for over 2 weeks or so, then what will happen is when you come back and you have a candy bar, it's going to taste extremely sweet. So these old cells have been replaced by the new ones, and the new ones have to get used to sugar now. B is supporting cells. That's going to be the little transitional cells there. Transitional cells are supporting cells. You see that they're in between the gustatory cells. So supporting is S-U-P-P-O-R-T-I-N-G. So it says specialized epithelium which forms the capsule of the taste bud and supports the gustatory cells. C is basal cells. There it is again. B-A-S-A-L. Produces new gustatory and supporting cells. So you see the profile, the way that these are set up between the nasal epithelium, the olfactory epithelium, and the taste buds is very similar. Taste buds are monitored by cranial nerves. Number 8, that's the facial, 9 glossopharyngeal, and 10 is vagus. Number 2, types of papilla. Papilla are elevated areas on the tongue, some of which contain taste buds. They don't all contain taste buds. Some of them do, some of them don't. So look at A, like this right here, filiform papilla, F-I-L-I-F-O-R-M, papilla. Slender thread-like pointed projections which cover the anterior surface of the tongue, pretty much the whole surface of the tongue. They give the tongue a friction surface to move food around in your mouth. This is how when you're chewing food up in your mouth, you just kind of pay attention next time you're chewing something, and you'll notice that your tongue is moving and is pushing the food over your teeth. And the way that it can do that is it has a whole lot of these filiform papilla, which will be a friction surface to move that food over your teeth. B is fungiform papilla. It's right here in the middle. F-U-N Giform. That means fungus shaped. And mushrooms are a fungus. So you look at the definition. Knob-like or mushroom-shaped papilla on the, it says tips and sides. They're also on the surface of the tongue. And most of these bunchiform papilla contain taste buds. Most of them do. The third type are called circumvallate papilla. CIRCUMVALLATE papilla. Circumvallate. And these look like little round donuts on the back of your tongue in an inverted V. And so what it says here is circular donut-shaped papilla arranged in an inverted V on the posterior portion of the tongue. Now you can look at this. You can see these on your tongue if you open your mouth real wide and you get a flashlight and you shine it in the mirror, not in your mouth. It'll block your vision. Shine it in the mirror and it'll reflect and light up the inside of your mouth, and you can see these pretty easily on the back of your tongue. Vision, the ability to detect light and form detailed images. Okay, that's pretty obvious. Number one is accessory structures. So structures which support and protect the eyeball. Those are called accessory structures. And the first one is your eyelids. And up here at the top, you can see this top picture of the eye. There's your eyelid. You know what eyelids are. You have an upper and a lower. So A is eyelids, EYELIDS. Also called palpebrae, a skin flap which lies over the eyes, periodically blinking. They shade the eyeball, spread fluid over the surface of the eye, and protect the eyeball from debris and drying out. So that's what they're doing when you blink. It keeps the surface of your eye moist and clean, cleans the surface of your eye, and sweeps the lacrimal fluid, which is produced by the lacrimal gland, medially. So over the day, that fluid is going across your eye from the lateral surface to the medial surface and drained off. Yeah. The palpebral fissure, F-I-S-S-U-R-E, that's the opening that your eye sees through when your upper and lower eyelids open up. The upper one raises and the lower one goes down. It exposes your eye. Your eye is looking through the palpebral fissure. So this definition here is the opening between the upper and lower eyelids. The two eyelids join at the corners of the eye. These areas are called the medial and lateral canthus. And here's the medial canthus right here. I've got my little pointer out. And the lateral canthus is the other corner of the eye. So those corners are called a canthus, C-A-N-T-H-U-S. The eyelash, you know what eyelashes are short, stiff hairs embedded in the outer margins of the eyelids. They prevent dust and debris from falling into the eye and will cause a blink reflex when they're touched. If you're out in a lot of wind and stuff's blowing around, something will touch your eyelashes and cause you to blink. You didn't do that on purpose, but something touched them, and it's a reflex which prevents objects from falling into your eyes. Along the inner margin, which you really can't see on any picture that we have here, but on the inner margin, a little fleshy margin there, upper and lower, of the eyeball are meibomian glands, M-E-I-B-O-M-I-A-N glands, which secrete a lipid-rich substance which prevents the eyelids from sticking together. That's why when you go to sleep and your eyes close, when you wake up, they're not stuck together. The lipid won't form a crust. It allows it to stay slippery, and so your eyes can open up. The lacrimal caruncle, that's that little flesh pad in the medial canthus of your eye. You look over here, there it is, lacrimal caruncle. I'm circling it now with my little hand. And there it is, that little flesh pad. So a fleshy pad which contains glands which secrete a thick kind of secretion. It's kind of, a lot of mucus collects there, but it secretes a thick secretion to help lubricate the eyeball. Bacterial infections of meibomian glands produces a small lump called a chalazion. And a chalazion is the same thing as something we're going to talk about in just a minute called a stye, if you ever had one of those. An infection of a sebaceous gland of the eyelashes, a meibomian gland or sweat gland of the eye, produces the painful localized swelling called a stye. Those are little bumps you'll see, and they are kind of painful. Your best bet is to put a warm, moist compress on those to help loosen it up so that you can get rid of or open up the gland and drain it. Otherwise, you have to go to an optometrist and get that taken care of for you. The orbicularis oculi, which again you can't see on this, but you know where that is. Orbicularis means circular. Oculi is around the eye. So you've seen that when you were on the muscles, you saw that one. Are responsible for closing the eye. And the levator palpebrae, which you really can't see here on this slide here, is this muscle up in here in this upper eyelid up there. Okay. Levator palpebra superioris is responsible for raising the upper eyelid. Yeah. Now there's a thin mucous membrane called the conjunctiva. conjunctiva covers the inner surface of the eyelids. So it's on the back side of your eyelids, and the anterior surface of the sclera, the white of your eye, up to the margin of the cornea, basically where you can see your iris. Conjunctivitis, if you ever heard of that, that's called pink eye, is an inflammation of this membrane due to trauma or pathogenic infection. Now, when you have pink eye, that irritation of that membrane will cause a crusting of your eyes when you sleep. So you'll wake up and have to remove that crust so you can open your eyes easier. So conjunctivitis and pink eye are the same thing. It's very contagious. So you gotta be careful. It passes very easily. The cornea. Now on this picture, you see over here on the right, there's the cornea. On the surface is very clear and transparent. So cornea is a transparent surface structure on the front of the eyeball. Now they can do corneal transplants, and I'll talk about that in just a little bit. B, lacrimal apparatus. So let's go and look at the lacrimal apparatus. It's LACRIMAL, second word, APPARATUS, produces, distributes, and removes tears. This is going to support the eye. A pocket called the fornix is formed where the palpebral conjunctiva meets the ocular conjunctiva. So let's look back over here again just for a second. Let's look at the eyelid here. Here's an eyelid. Well, there is conjunctiva on the eyelid, the back of the eyelid, and on the white of the eye, all the way up to the cornea. On your lower eyelid and on this upper eyelid, conjunctiva, all the way up to the cornea. Okay. And the ocular conjunctiva is going to cover the cornea. The lateral portion of the superior fornix receives some ducts from your lacrimal glands. So we have to go back again now that we know that there's a pocket up here between the eyeball and the back of the eyelid. Here's your lacrimal gland. It's going to be superior and lateral on your eye. And there are your lacrimal ducts, which are going to secrete lacrimal fluid onto the surface of your eye to clean and protect your eye. So there are 10 to 12 of these little lacrimal ducts from each of these lacrimal glands. Lacrimal glands are located on the superior lateral aspect of the eye. There it is again. And produce about 1 ml of lacrimal fluid or tears per day. These tears reduce friction because it's slippery and has mucus, removes debris, it sticks in the fluid, prevents bacterial infection because we're going to see that there's an enzyme in there, and provides nutrients and oxygen to the conjunctiva. These secretions are watery, slightly alkaline, and contain the enzyme lysozyme, 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 which bursts bacterial cell walls. to lysis, to destroy. Enzyme is an implication, it's an enzyme. Blinking sweeps tears over the surface of the eyeball toward the lacrimal puncta. Now the lacrimal puncta are going to be on the medial aspect of the eye, and look at this picture on the right-hand side. See where my pointer is? Lacrimal punctum, that's the one in the upper eyelid. The one in the lower eyelid, this little dot, is not labeled. So you can see these openings that are going to drain off the lacrimal fluid or the tears. Okay, so blinking sweeps tears over the surface of the eyeball toward the lacrimal puncta, those two openings. Now girls probably see that because when they put makeup on around their eyes, they probably have seen those. Guys probably never seen them in their life, but that drains tears off. So these puncta drain tears into an upper superior lacrimal canal. If you look at this right here where I'm pointing, superior lacrimal canal, or canaliculus there, is this canal is going to be a little tube that is connected to that punctum from the superior punctum, and one coming off the inferior punctum right there. So those are the superior and inferior lacrimal canals. These canals deliver tears to a nasolacrimal sac here, which is the NASOLACRIMAL, well, duct, and then the sac is right there. And then tears drain into your nasal cavity. So when you have irritation of your eyes or when you cry, the mucus gets wet and you're sniffling tears, and moistened up mucus is loosened. Let's look at the eye. Here's an eye. The visual organs which contain the receptors for vision. We'll talk about that in just a second. They're located in the two orbits of the skull. That's pretty obvious. About 1 inch in diameter, and share the orbit with extrinsic eye muscles. Now, the extrinsic eye muscles, you're going to look at those more likely on a slide in lab. So I'll leave it at that right now for this. So again, I don't have anything that really shows much. I have this slide. It shows the medial rectus and the lateral rectus. So the nose is right there. That's 2 of the 6 extrinsic eye muscles. Okay. So shares an orbit with the extrinsic eye muscles. Fat, see there's fat behind the eye, orbital fat, for padding and insulation. The lacrimal gland, which you have to look again back into another slide, which kind of shows that gland, superior and lateral on the eye. Okay, blood vessels and cranial nerves. You have about 5 cranial nerves that go to supporting the eye. You know, the one you think about the most is the optic nerve, number 2. But then you have some other ones too, if you remember the cranial nerves. The fibrous tunic, over here on the right on this slide, the outermost layer of the eyeball, which consists of the sclera. The sclera is the white of the eye, and the cornea, the clear transparent surface on the front of the eye. So that fibrous tunic is made up of those 2 parts, the sclera and the cornea. The sclera is a dense, white, fibrous coat, contains collagen and elastic fibers, which is tough enough to prevent puncturing, helps to maintain the shape of the eyeball, and is the point of insertion of those 6 extrinsic eye muscles. That's what they attach to move your eyes around. So it has some pretty good functions. Prevents puncture, maintain the shape of the eyeball, and is a site of attachment for your extrinsic eye muscles. They insert there. The cornea on the surface, up here at the front, clear transparent cornea, and you can see right through it, and you see the iris behind it, is a clear transparent avascular, A means without, continuation of the sclera. So it differentiates. The sclera differentiates from white, opaque, collagen and elastic laden to a clear transparent surface called the cornea. It contains many free nerve endings, which make it very sensitive to chemicals, touching, and drying, which you know that your cornea is kind of sensitive. The junction between the sclera and the cornea is called the limbus. Now let me change slides for just a second. I think I have it right here. right there. See my finger up here? Limbus, Limbus. It's a transition zone between the sclera, which is white, opaque, and pretty tough for puncture, and the clear transparent cornea on the surface of the eye. And we'll look at this little vessel in there later. There's a vessel in that transition zone. So where it transitions from the sclera to the cornea, that area is called the limbus. Corneal transplants are possible due to the fact that there are no blood vessels to carry white blood cells to this area to attack a foreign tissue. Since they're avascular, they don't have a blood vessel system attached to them. They get their nutrients through lacrimal tears and through something we're going to look at in just a little bit called aqueous humor. Let's look at the next one. Switch my slides again. Over here on the in the middle kind of this picture, the vascular tunic. Now, uvea is an old term I will never ask. You probably never see that again. So it's the vascular tunic. It's called vascular, V-A-S-C-U-L-A-R, because it contains blood vessels, the intrinsic eye muscles, and lymphatics. So we're going to look at an intrinsic muscle in here. There's two of them in here. This layer of the eyeball includes the iris. There it is, the iris. That's what's pigmented on the front. You have a brown eye or a green eye or a hazel eye or a blue eye. That's on the front of the iris. An intrinsic muscle of the eye. So the iris, I-R-I-S, is a muscle. And let me just read this and we'll change slides in just a second. It's pigmented on both the anterior and posterior surfaces. All right. Here is a person whose iris has been dilated here, but the pupil has been dilated, so you see a big pupil there. Some muscle fibers are pupillary constrictor muscles, which are these circular ones here. You can see them on all three pictures. But when they contract, since they're a sphincter, when they contract, it's going to close that opening called the pupil. The pupil is an opening. And radial muscle fibers, which are the ones that go from the center of the circular iris to the outside, when they contract, they're going to open the pupil or pull it and make it larger. The picture on the left. Change the diameter of the central opening or pupil, P-U-P-I-L. Now the ciliary body, let's look at a bigger picture here. Ciliary body, C-I-L-I-A-R-Y, body, begins at the junction of the scleral and cornea, where they kind of differentiate, and extends posteriorly to the ora serrata. Now, this blue structure here is part of this ciliary body we're going to talk about in just a minute. So here is the ora serrata. It's not labeled on this picture. Ora means circular. Serrata means sawtooth. And see, it's a jagged sawtooth circle. It goes all the way around the inside of the eyeball in a circle. So ora, O-R-A. Second word, serrata, S-E-R-R-A-T-A. The ciliary body, there it is again, ciliary body, contains the ciliary muscle, which is this muscle right here. It's not labeled, but that's the muscle right there. And the ciliary process, these little blue structures here. And they cut this top of the ciliary processes, these little wiggly lines here. So these are the ciliary processes here. You'll see that better on a model in lab. The ciliary muscle is a sphincter muscle, so it goes all the way around, which lays under the finger-like epithelial folds called ciliary processes. So this is underneath these ciliary processes. And when it contracts, it's going to decrease the tension on these structures here. We'll talk about in just a second. The suspensory ligaments, that was several seconds. Suspensory, S-U-S-P-E-N-S-O-R-Y, ligaments, there they are. They're going from the ciliary processes to a capsule around the lens. Suspensory, so they're suspending this lens in the middle of the eye behind the pupil. So it's called the suspensory ligaments. So suspensory ligaments of the lens extend from the capsule covering the lens to the ciliary processes. The ligaments help to hold the lens behind the iris and centered with the pupil, P-U-P-I-L. I'm sorry, I get to lecturing instead of looking at my notes. The choroid coat. Well, let's look at another slide here to see the choroid coat. The choroid coat is going to be a heavily pigmented layer. You see it's right here. It's this light tan layer here. It's heavily pigmented, okay, layer which separates the fibrous and neural tunics. Okay, so it's part of the vascular tunic, and on the innermost tunic is going to be the neural tunic or the retina. So it's right below that. This layer contains many capillaries which supply the retina with oxygen and nutrients and remove waste products. It's also heavily pigmented, so the back of the iris is going to be kind of a black or purplish color. The back of the suspensory ciliary processes, they're going to be heavily pigmented, so they'll be dark. And the inside of your eye is going to be dark. That's why everybody's pupil is black, because this choroid layer makes it dark inside of the eye to prevent light from refracting around or reflecting inside the eye. It absorbs the light. You know, an albino rabbit, they don't have a choroid coat that has any pigment in it, and they have pink eyes. That's why they have pink eyes. A non-albino rabbit does not have pink eyes. They have black pupils. The third tunic that we could look at is going to be called the retina. See, it's the neural tunic or the retina, right down here. R-E-T-I-N-A. Consists of an inner neural retina, okay, which contains many photoreceptors for vision and an outer pigmented layer. So here is the retina here. This is the inside of the eyeball where this light's coming through. You see that there's several layers of cells here. And look at that back layer, pigmented part of the retina. You see a drawing on the left and the real one on the right. The neural retina's primary function is image formation. There are 3 zones of neurons in the neural retina, and you can see them here, just in case I don't point them out. Here are the bipolar neuron. These are ganglion neurons here. Here's the bipolars here, and then the photoreceptors here, rods and cones. So there's 3 layers. The innermost zone contains photoreceptor cells, receptors of light, photoreceptors called rods and cones, R-O-D-S and C-O-N-E-S, cones. These receptors are actually modified ends of dendrites. Here are the modified ends of dendrites. Here's the rod, which is shaped like a rod, and the cone, which comes to a blunt tip. So you can see that they both are shaped somewhat differently. Rods are cells responsible for black and white vision. So these rods are for black and white vision, are somewhat cylindrical in shape, and are specialized for dim light or low light conditions. Cones over here on the left are conical shaped, are somewhat conical shaped, and function in color vision and for sharpness of vision. They require more light than rods in order to function. That's why you don't see light at night. If you are walking around at night and you look at something in particular, you're not going to see exactly what you're looking at. You'll see peripherally, but you're not going to see what you're looking directly at. Try this and look at an electric socket tonight. Look at it. You won't see the holes in the socket. You look off to the side and you will see the holes, because when you look at the socket, remember the well, you don't know this yet, but you're focusing on an area that is pretty much mostly cones. That requires a lot more light to activate, and there's not a lot of light in the room when the lights are off. So you look to the side, and your peripheral vision, which the area around where your critical vision occurs, has a lot of rods in it, and so you're able to see those dots in your peripheral vision. But what you're looking straight at, you won't see. There are approximately 125 million rods around the periphery of the eye compared to around 6 million cones located on the posterior retinal surface. Back here on the back, look at the bottom of this picture where I'm a little pointer here, area called the fovea. So a shallow depression called the fovea, F-O-V-E-A, centralis, C-E-N-T-R-A-L-I-S. This is an area of just cones on the retina. It's a little divot, little dent in the retinal lining there. Can be found on the posterior surface of the eye. This is an area of the retina. See, it is a part of the retina, which covers the fovea, called the macula, M-A-C-U-L-A, macula. So they are both parts of the retina. And the fovea is like a large ring, and right inside of that is the macula lutea. Macula means spot, lutea means yellow. So it appears to be slightly yellowish when an optometrist looks in your eye and looks at your retina. They can tell where your macula lutea is very easily. The macula is composed, that should be mostly of cones. Not entirely, but mostly of cones. The visual axis, which you see here, right in the middle, this white arrow in the middle, is always focused on the macula lutea, right there where your critical vision is. Critical vision occurs on this macula area. Now, whatever you're looking at, birds in the sky, words on a piece of paper, if you're painting someone's face, whatever you're looking directly at is focusing right there, okay, on the macula lutea and fovea area. All the rest of what you see in your field of view is due to your peripheral vision, the rods and cones and the rest of the retina. There's a problem called degenerative macular syndrome, and it has to do with blood vessels building up where this macula is, and you start going blind because it destroys the retina. My dad had that, and they gave him shots in his eye to prevent or reduce the blood vessel formation. So there are ways to treat this if you catch it in time. So it says the visual axis right there is always focused on the macula lutea. Critical vision occurs on the macula area. The rods and cones synapse with approximately 6 million bipolar neurons. So here are your rods and cones, and there are your bipolar neurons. So you see here's your rods and cones synapsing with your bipolar neurons, which in turn synapse with a layer of ganglion cells. There are your ganglion cells down here. The axons from the ganglion cells exit the back of the eyeball to form the optic nerve. Okay, so let's see that. Here they are. There's your rods and cones. There's your bipolar neurons. Here's your ganglion cells, and their axons are going out the back of the eye as cranial nerve number 2, the optic nerve. The area where these axons exit the eyeball is devoid. That means they don't have any photoreceptors for vision. So look right here. There are no photoreceptors here. So this area is called the optic disc or the blind spot, B-L-I-N-D spot, blind spot. Now let's look at some chambers of the eye. The lens, okay, it's just right there, and the ciliary body, which is the ciliary muscle and the suspensory, ciliary processes, sorry, divide the interior of the eye into the anterior and posterior cavities. Okay, the anterior cavity, look at the top of this picture, there's the anterior cavity, is divided into an anterior chamber and a posterior chamber. The anterior chamber, look at that line, it goes down, is between the front of the iris and the back of the cornea. So it's that space up in there. Between the front of the iris and the back of the cornea, there's going to be a fluid in that anterior chamber. The posterior chamber, which is the one on the left there, is the area between the suspensory ligaments, which are right there. Remember, they go around the lens. There's a capsule around the lens, and the back of the iris. So it's a little pocket there And so you see where that arrow is pointing. It's between the back of the iris and the suspensory ligaments, which go all the way around that lens. It's a pocket there. A fluid called aqueous humor, A-Q-U-E-O-U-S, humor is a fluid, H-U-M-O-R, is secreted by the epithelium of the ciliary process. So right here where these little arrows are coming out, that's the epithelium of the ciliary process. This fluid is continually being produced and is replaced about every 90 minutes. This fluid helps to nourish the lens and cornea. It acts as a type of a nutritive media or medium. Doesn't have any cells in it, no red and white blood cells. Is secreted by the epithelium of these ciliary processes. From the anterior chamber, the aqueous fluid drains into the scleral venous sinus. So let's follow this first. It's secreted by the epithelium of the ciliary processes. It goes into the posterior chamber, goes up, leaves by way of the pupil out into the anterior chamber, and it's going to exit by way of the scleral venous sinus. Canal of Schlemm is an old term. Scleral venous sinus is S-C-L-E-R-A-L, second word, V-E-N-O-U-S, scleral venous sinus, and then into the blood. So this is a little blood vessel right in the area of the limbus between the the sclera and the cornea. And that's a transition zone. That's where that scleral venous sinus is found. It's in the middle of the limbus of the eye. The intraocular pressure is mainly, it's produced mainly by the aqueous humor, this fluid that's secreted by the epithelium of those ciliary processes. Excessive intraocular pressure, too much fluid pressure in this anterior cavity, causes degeneration of the retina and blindness. It puts too much pressure on the back of the eye. Now the posterior cavity, this whole area behind the lens and suspensory ligaments, this whole area back here is the posterior cavity. P-O-S-T-E-R-I-O-R, cavity. Contains a thick jelly-like fluid called vitreous body, V-I-T-R-E-O-U-S. Things that are viscous or vitreous or thick. It's like egg white coming out of an egg. It has a consistency to it, or real weak jello. This fluid helps to prevent the eyeball from collapsing and holds the retina, which is the inside layer, right, inside tunic, flush, pressed up against the interior of the eyeball. Helps keep it nice and flat up against the inside of the eyeball. It's crystal clear and is not replaced. It says naturally, it is, but it's very, very slow. So the notes say not replaced naturally. It is, but it's kind of a slow replacement if you lose any. The lens. Well, let's look at the lens a little bit. Well, you can see it right there in the middle, right there. See the lens. Let me find another picture though. Here's one. Good one. The primary function of the lens, you can see in both pictures, is to focus an image on the surface of the retina, and that little pink dot is an image focused on the retina. In order to do this, it must be continually reshaped. There's a capsule around the lens to which the suspensory ligaments attach. When someone gets their lens replaced from cataracts or something, they'll shatter the lens, remove it, and remember the lens has a capsule, so the capsule is still there. And they put a plastic lens in its place. And that plastic lens is now held behind the pupil. It's not going to be reshaped or anything, but it's held in place behind the pupil. In near vision, N-E-A-R vision, the ciliary muscle contracts and the tension on the suspensory ligaments is lessened. Okay, I drew this little PowerPoint for you. So in near vision, the ciliary muscle, this is the red muscle here, so remember it's a sphincter muscle, contracts. So it's going to go in. It was out here, out, it goes in. It's going to make the opening smaller, right, when it contracts. And that, because it does that, the tension on these suspensory ligaments is lessened, and the tension on that lens is lessened. It allows the lens to become more biconvex, more fat, a more convex shape to it. So here's the muscle. There's a ciliary process there, the little black thing. There's your suspensory ligaments, and you see that the lens is real nice and biconvex. I put this picture on here because it said this muscle contracts and the tension's released. Well, it's released because the ciliary muscle is a sphincter muscle, and when it contracts, it goes in like this. And if you have ligaments that are going like this attached to the periphery of that lens, they're going to go in too, and the tension is going to be reduced. Now that lens is like a piece of really, really soft plastic. I mean, it's not plastic, soft rubber. Like those things you get at Chuck E. Cheese that has a long little string and has a hand on the end, and you throw it and it sticks to stuff. It's that soft. It's really soft. It's a little bit larger than a BB, between a BB and a P. Really soft, and it can be reshaped very easily when you're young. In far vision, the ciliary muscle relaxes, so it's going to go out. It's going to expand, like it's going to go out like this. When it does, it's going to pull on those suspensory ligaments, which pulls on the capsule surrounding that lens. And then you can see on the right-hand side, it's going to flatten that lens out some. So in your reading, it says in far vision, FAR, the ciliary muscle relaxes, and the tension on the suspensory ligaments increases, tight, resulting in the lens being pulled, which reshapes the lens into a lesser biconvex shape. It's not as bowed out as it used to be. This process of reshaping the lens to compensate for near and far vision is called accommodation. 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 Now light, you can see over here, just follow these little lines, you can see this bent. Light is bent or refracted when it passes between media of different densities. And you can see that real well if you get a glass of water halfway full and you put a straw in there and you look at it on the side, you see that the straw is going in here and the other part of the straw is over here like this. The light's just traveling through air and water at different rates. They have different densities. The greatest amount of refraction or bending of the light occurs when light passes from the air into the corneal tissues, into the cornea. There it is on the front of the eye, which have a density close to that of water. Additional refraction or bending takes place when the light passes from the aqueous humor into the relatively dense lens. The lens provides the extra refraction or bending needed to focus the light rays to form an image on the back of the retina. So it says to focus the light rays from an object toward a specific focal point. That's where it's going to be in focus on the back of your eye. The distance between the center of the lens and the focal point is called the focal distance. Just the definition. If the cornea and or the lens, and I've been told the cornea is the main culprit for this, has minor imperfections, it's not smooth, but it's kind of wavy, or irregularities in its shape, it will not be able to uniformly reflect light entering the eye, and therefore, the image focused on the retina will not be uniformly focused. This is called an astigmatism. This is where you have a blurred vision in a particular area of your vision is kind of blurry. That tells the optometrist you have an astigmatism, and they can get lenses that will take care of that for you, or you can go in and have it fixed. Another property of the lens is due to its biconvex shape. The image is inverted on the retina. A biconvex lens has a property of turning objects upside down and backwards. So on the back of your eye, since you have a biconvex lens, the image of everything you see is upside down and backwards, but your brain reverts it right side up and forwards. So the visual center of the brain corrects this problem. Now we have some visual problems here on this slide here. And let's see, emmetropia is normal vision, that's A. So you see the light coming in is focused right there on the retina. Number 2 is myopia, M-Y-O-P-I-A. Now look at that, it's not focused, it's focused in front of the retina. So let's look at the definition, nearsightedness. This results if the eyeball is too deep, see it's oval instead of being real round, or the resting curvature of the lens is too great, is too biconvex. The image of a distant object will be focused in front of the retina, so that's where it's actually in focus. And so what's being focused back here on your retina is not in focus and it's blurry. You don't see well. You'll have difficulty seeing distant objects clearly, but you'll be able to see well for close-up things like reading. And you can see down here, myopia corrected. They put a corrective lens in your glasses, which pre-bends the light to the degree necessary to focus that image on your retina. So your glasses or contacts will do that pre-bending of the light so it focuses correctly on your retina. Hyperopia, number 3, or farsightedness, results if the eyeball is too short. See, it's not real round, it's less rounded. Or the lens is too flat. The lens is too flat, not very biconvex. The image of a distant object will actually be focused behind the retina. So it's going to be blurry here because it's actually being focused behind the retina. This is hard, I have in my notes, hard to focus to read close up, but you can see far off objects fairly well. Now I have hyperopia, obviously, because I can see far off pretty decently, but I'm wearing these so I can read my notes. So myopia and hyperopia are problems with the shape of the eyeball. Well, I also have something called presbyopia, which has to do with the condition of the lens, not the shape of the eyeball. So presbyopia, number 4, P-R-E-S-B-Y-O-P-I-A, a loss of the elasticity of the lens. So the ciliary body, when it works, when the ciliary muscle contracts and it pulls on the ciliary processes which pull on these suspensory ligaments, which are pulling on the capsule around the lens, my lens is not flexible anymore, so it can't be reshaped. And that happens in older people, usually 40 plus, usually. And they end up either having to wear glasses for seeing far off or these reading glasses for seeing close up. So presbyopia, P-R-E-S-B-Y-O-P-I-A, the loss of elasticity of the lens usually occurs in older individuals, and most of the time it results in hyperopia. Okay, most of the time it's going to result in what's called hyperopia. Visual physiology. So let's look up at another slide up here for the physiology. Back over here to the rods and cones. The rods and cones of the retina are called photoreceptors. Remember, photo is light, and receptor is a type of receptor. So they're receptors for light. They're sensitive to wavelengths of 400 to 700 nanometers, which is the visible spectrum of light. From general biology, you remember the visible spectrum, the Roy G. Biv, like a person's name, red, orange, yellow, green, blue, indigo, violet. Rods and cones are named due to the shape of their outer segment. So you can see the rods here are somewhat rod-shaped when these discs are stacked, and the cones are more blunt. These outer segments contain thousands of discs which contain, rods, I'm sorry, go back. Rods and cones are named for the outer segment. These outer segments contain thousands of discs which contain molecules called visual pigments. In a rod, each disc is an independent structure. So there it is right here. It's like a little hamburger. You can see the 3 discs there stacked. And a whole bunch of them are stacked on these rods here. So it says each rod, in a rod, each disc is an independent structure as a result of disc being stacked like a whole bunch of pennies, making that stack there for the rod. Gives the rod a cylindrical structure. In cones, the discs are the result of the membrane being folded, which results in the outer segments forming a blunt tip. That's why they're conical, so they're called cones. Now look over here on the right-hand side. The visual pigments are composed of a compound called rhodopsin, R-H-O Dopsin. This compound contains a protein called opsin, and there it is, Opsin, which is bound to a pigment called retinol. There it is too, retinol, which is synthesized from vitamin A. Okay, vitamin A supplements can increase your night vision a little bit, make it a little better than it is. It's not going to give you super night vision, but it helps for people who have night vision. There are 4 types of opsin, okay? 4 types of opsin that make up these retinols. One is used by rods, which results in black and white vision, okay? Rods are the photoreceptor for black and white vision. The other 3 are used by the red, green, and blue cones, which result in color vision. So there are 4 opsins, and that makes that there are 4 different rhodopsin molecules. The rhodopsin of rods breaks down quickly in the presence of bright light and reforms slowly, which again is why when you turn the lights out at night, you're basically blind for a while until the rhodopsin in the rods slowly builds back up, and the breakdown is not as fast as the buildup. And so you can always have the rhodopsin for your rods working. After a few, several minutes, 20, 30 minutes, you can see fine in the dark, but it's black and white. The rhodopsin of cones breaks down quickly. Okay, so it's going to break down fast, but it's also going to form fast, reforms fast. So you don't ever really lose your color vision. Lights on, see color vision. Off, you don't see. Back on, you see color again. So the only reason you don't see a color when the lights are off is that there's not enough light to activate the cones. The rods are low light photoreceptors. Cones are moderate to bright light photoreceptors. The breakdown of rhodopsin into retinol and opsin is called bleaching. So it's constantly being bleached and constantly being built back up. If you are driving down the road and the sun hits someone's bumper or someone's back windshield, like on a truck, and it flashes in your eyes and you see spots, or you can see that bumper, or you can see the word Ford, you've bleached out very quickly. You've bleached out a lot of the pigments. You're seeing what's called after images. And until those rhodopsin molecules reform, you're going to have that imaging, after image. Equilibrium and hearing, all right, has to do with your ear. Equilibrium informs us as to our position relative to gravity, as well as to our movement through space. Hearing allows us to perceive and interpret sound waves, and our equilibrium and hearing is very precise in people's bodies. Some exercise those receptors a lot, use them a lot, and they become very efficient at balance, like gymnasts, stuff like that. People who can walk beams or do gymnastics, they have a lot of motor controls, motor skills. Basketball players, good motor skills. Football players, soccer players, very good motor skills, and part of that is due to equilibrium. So let's look at this little picture here, and up here at the top, see external ear? I'm circling that right now. Consists of the external pinna or auricle, A-U-R-I-C-L-E, which captures sound waves and channels them into the external auditory canal. That's the ear hole on the side of your head. This canal is lined with ceruminous glands, which produce a waxy secretion to trap dust and debris and act as a bactericidal agent. It does keep bacterial count down, it kills them, and has short hairs which keep larger debris and insects out of the ear. They're kind of like bristles in there, but they're kind of deep in your ear hole. You would need a scope to see them, basically. The sound waves eventually cause a thin concave membrane called the tympanic membrane, T-Y-M-P-A-N-I-C, membrane, or eardrum, to vibrate back and forth. So the parts of the external ear are the auricle, the external auditory canal, and the tympanic membrane. Now, it said that the auricle captures sound waves and channels them into the external auditory canal. And you know that that works, because when you do this, you can hear a little bit better, especially when you do it with both hands. You're capturing more sound and you channel it into your external auditory canal, which makes the very thin tympanic membrane vibrate. Sound waves make it vibrate. Like a big truck going down the street, sometimes it makes, or an airplane or helicopter flying kind of low, it makes the windows vibrate. Same thing, sound waves make them vibrate. So those are the external ear components. We'll look at the middle ear, and I'm circling that in the middle of the picture at the top, middle ear. Also called the tympanic cavity, is basically air-filled because of this connection with the back of your throat, the auditory tube here. This is an air-filled chamber here. This area contains 3 bones called the auditory ossicles, and there it is. Auditory, A-U-D-I-T-O-R-Y, ossicles, O-S-S-I-C-L-E-S. Os means bone, and ickle means little, so they're the little bones of hearing. The handle, and we'll look at these again, they're bigger, but the handle of the mass, the first of the 3 auditory ossicles, attaches to the tympanic membrane, and the head connects to the second one called the incus, which is shaped like, actually reminds me of a tooth. Malleus is like a mallet. Incus, it has 2 root-like structures. You can only see one here. So that's the middle one. The incus in turn attaches to the stapes, which does actually look like a stirrup. Now let me see, I think I've got them over here. Actually, wrong way. Nope, don't have them on this one. Malleus, incus, and stapes, you can see them right here. Tympanic membrane, there's the malleus, the incus, and the stapes. It does look like a stirrup. See down here? It does look like a stirrup on a saddle. The 3 bones. The incus in turn attaches to the stapes, which fits on the surface, oval surface to the oval window. O-V-A-L-W-I-N-D-O-W. Now, this points out foot plate of the stapes at the oval window. Well, I put an extra slide in your slide set here. It's not in your normal one. It's only on this one. And there's the oval window, and you see it is oval shaped. That's why they call it the oval window. And the stapes fits on there and sends shock vibrations of sound into your inner ear for hearing. An auditory tube or eustachian tube, let's go back then. We got to go back to this picture right here. Here's your auditory tube or eustachian tube, that's an old term, or pharyngotympanic tube, another term, leads from the pharynx. The pharynx is your throat. That's what pharynx means. It's not pharynx, it's pronounced pharynx. To the middle ear, so it's an opening there, a tube, and functions as an equalization of ambient air pressure with the middle ear. Ambient is the pressure around you. So when you're in an elevator, you know your ears will hurt because the pressure is changing as you go higher into the atmosphere. When you swallow, it opens this tube, and the ambient air pressure in your mouth and your throat equalizes with the pressure behind your tympanic membrane in this atrium here. And when you go diving or something like that, pressure pushes on the tympanic membrane, and you're breathing compressed air, and you can hold your nose and open this up to force more air back here. So you have compressed air back here because you have high pressure from water on the other side of the membrane. So that auditory tube helps to equalize the pressure of the middle ear. The inner ear, this structure here that has loops on one end, a connecting part here in the middle called the vestibule, and then this snail shell coil here called the cochlea. And I have another picture right here of this model that we have in lab. The inner ear, the area responsible for equilibrium and hearing, there are 2 main divisions, the bony or osseous labyrinth and the membranous labyrinth. Okay, well, I got this picture here. This is one I was looking for in lecture in the Q&A today. But you see right here where I have this, this little black circle here. If you cut across, you got a cross section of this loop structure here called a semicircular canal. It's going to be the same wherever you cut it on this inner ear. There's an outer osseous labyrinth. A labyrinth means a maze, and you see it has a loop here and it has a coil over here, so it's a maze-like structure, and this is embedded in bone, so the outside shell is bone, osseous labyrinth. There's an almost identical membranous labyrinth that follows the whole thing on the inside. The spiral here, and each one of these canals, these loops, has a membranous labyrinth, which you can see right there. I've drawn this little gray line here for showing the membrane of the membranous labyrinth. Okay, so it says the osseous labyrinth surrounds the entire inner ear. Within the osseous labyrinth is the membranous labyrinth. There it is. Forms an almost identical copy. Between the osseous and membranous labyrinths is a fluid similar to cerebrospinal fluid called perilymph. P-E-R-I-L-Y-M-P-H. It's pink here, and it's also pink on the model. You can see it there. It's between the osseous and the membranous labyrinths. It goes all the way around the membranous labyrinth. Inside of the membranous labyrinth is another fluid called endolymph. E-N-D-O-L-Y-M-P-H. Endolymph, fluid within. So it's the fluid inside here. So there's two fluids. The perilymph is between the osseous and membranous labyrinths, and the endolymph is inside of the membranous labyrinth. All right. There are three areas of the inner ear. The first one, number one, is semicircular canals. They're not complete circles, so they call them semicircular, these three loops, 1, 2, and 3. So number one, semicircular canals, a series of three loop-shaped structures all arranged at 90 degrees to each other. Now, I'll just tell you what these are. This top one here goes, this is the front. This spiral that goes forward, that's the front of this inner ear. So this loop goes front to back. It's called the anterior semicircular canal. This one goes out to the side and back towards it. Out to the side is the lateral semicircular canal. And the one in the back, that forms a loop in the back, is called the posterior semicircular canal. Okay, so those are the three canals. At the base of each canal is a swollen base called an ampulla. Now there's an ampulla there. Let me see. I brought this picture here. You can see the ampulla pretty well. The swollen base. There's a one on each of the semicircular canals. There's one ampulla. Now inside of these ampulla, and inside the membranous labyrinth of that, you're going to see a receptor, which is called the cristae. Now here they are, and here's the ampulla. Here's an ampulla. Here's an ampulla, and the receptors are inside. You see they're inside of the light blue, the membranous labyrinth. So this is the membrane of the membranous labyrinth here. And you know that the fluid inside of there is going to be endolymph. And here is the receptor here. So within the ampulla are receptors called cristae, C-R-I-S-T-A-E. Now single is crista, which you can see right there. These structures are responsible for interpreting movement through space, such as accelerating, rising, or falling. This type of equilibrium is called dynamic equilibrium. So these cristae are the receptors for dynamic equilibrium. They're the receptors. And you see they have a cupula. It's a gelatinous top. Let me just read through this. The hairs of the cristae, so see here are the hair cells, and they're their hairs down here, have 80 to 100 long stereocilia. Those are going to be the short ones. And then there's one large kinocilium coming off that goes deeper. So we really can't see the stereo. We can see one here, probably kinos on this picture, are projected into a gelatinous cap called the cupula, C-U-P-U-L-A. Now, when movement through space occurs, when you move, we'll see it here, movement through space is occurring, endolymph flows past the crista and causes the cupula to be displaced. It causes it to bend over to the side. This distorts or pulls on the hairs, pulls the cilia of the hair cells, which cause an impulse to be generated and sent by way of the vestibular branch of the vestibulocochlear nerve, number 8, to the brain for interpretation of movement in a particular direction. So see, you're at rest here, movement in a particular direction is going to cause this endolymph to flow past these cristae, push on the cupula, which bends to the side, which bends the hair cells, and the bending of the hair cells triggers an impulse. And that impulse is going to go by way of the vestibular branch of the vestibulocochlear nerve to the brain for interpretation of movement in a particular direction. So remember, they're located in all those semicircular canals, and those are at 90 degrees to each other. Now the other receptor we saw here, these called macula. So this area contains two swollen, let's look at number 2, vestibule. So let me find the vestibule shot on that I have for you on here. Right here. It's the top of the vestibule. An area involved in equilibrium located between the semicircular canals, there are the loops there, and the cochlea, the spiral shell structure here we'll look at last. So the vestibule has 2 bumps on it, the utricle and the saccule. Always kept those straight, like United States, U.S., utricle, saccule, which contain another type of receptor that we're going to look at next, called the macula, and here they are. So these receptors here, the macula, M-A-C-U-L-A, are found in the utricle and saccule. These receptors, the macula, inform you as to your orientation relative to gravity, your upright nature. You know, you can stand upright because of this receptor here. It tells you what upright is. It also tells you when you're leaning. When you lean to your head to the side, if you look at your little picture here, these otoliths on top are going to be pulled by gravity, and let's say this way to the right. It's going to cause this membrane to be pulled with the otoliths, which bends the hair cells and triggers an impulse that's interpreted by your vestibular branch of the vestibulocochlear nerve. It goes to your brain to be interpreted as you're tilting in a particular direction, and so you'll straighten yourself back up. That's how you know you're straight up. So let's look at the reading here again. These receptors inform you as to your orientation relative to gravity. That's called, it's not in your notes here, I just saw I missed it. It's called static equilibrium. S-T-A-T-I-C, equilibrium. That's your orientation relative to gravity. It's called static equilibrium. This receptor has hair cells. There it is, got the hair cells, stereocilia, you can kind of see them there. The kinocilium. The cilia extend up into a gelatinous membrane. They call it gelatinous material here, which is covered with calcium carbonate crystals called otoliths. Calcium carbonate is like calcium carbonate like in shells, but you have crystals that are sitting on top of this gelatinous membrane so that when your head tilts, the crystals are pulled by gravity. Let's say again to the right here, pulls on the membrane, which the hairs are embedded in. So they're pulled to the side, and that generates an impulse that says you're leaning in a particular direction. This is what these two senses are what roller coasters mess with, get you all mixed up when you're on a roller coaster. When the head is tilted, the otoliths cause the gelatinous membrane to shift, which distorts or bends the cilia, causing an impulse to be generated. The impulse is sent by way of the vestibular branch of the vestibulocochlear nerve to the brain for interpretation of leaning in a particular direction. Let's look at the last part of this inner ear, and it's going to be this part over here called the cochlea. See over here on the far right, cochlea. It's a snail shell. And you can see from the bottom of this cochlea area, you see the membranous labyrinth going right in the middle, kind of. It's actually pushed to the side a little bit, but it's in the middle. So you see this blue, it's a light blue spiral going with the cochlea. It's on the inside. That's the membranous labyrinth. So number 3 is cochlea, the portion which is coiled like a snail's shell. The structure contains 3 chambers. So if you were to cut it anywhere along that spiral, anywhere, you're going to see the chambers are going to be the same. And this has been cut. You see here's the spiral on the far right, and it's been cut, and here's the cut here. Here is one part of that tube. Here's another one up here, and they're identical. They're just at different distances along that tube. So we're going to look at this one here. The structure contains 3 chambers. The scala vestibuli, the scala vestibuli Yeah, our vestibular duct, yeah, is the duct which receives pressure waves from the stapes as it pushes on the oval window in response to sound waves, making the tympanic membrane vibrate. Yeah, vestibular duct is just not one that's used a whole bunch. Scala vestibuli is, but you can look on this picture here, and you can see that the stapes is pushing on the oval window and sending shock waves into this top chamber, and there it is. There's the vestibular duct or scala vestibuli. We'll call it duct since they do here. So the oval window is what the stapes is pushing on. Some of these pressure waves, which you can see here, travel to the end of the cochlea. All the way, this is uncoiled here, and the tip right there, which is also the tip which is right here, is called the helicotrema. So the very tip, the very end of the spiraling, that's called the helicotrema. So it can go all the way down this way. The pressure wave can go all the way down around the helicotrema and come on the back or lower chamber, which is called the scala tympani or the tympanic duct. It's called the tympanic duct because of this tympanic membrane that surrounds a round window. Now I have a picture that I put in here again. It's not in your regular slide set, but this one right here. There is your oval window, it's oval, and there's the round window. It is actually round, and it has a tympanic membrane on it that acts as a pressure relief valve, because you know that fluids can't be compressed, right? So when the stapes is pushing on the fluid, the perilymph in the vestibular duct, the pressure has to be relieved somewhere. And it's relieved over here on the tympanic duct side at the round window. There's a tympanic membrane there. So when the stapes pushes on the oval window, the round window's tympanic membrane gives. Like that. Okay? Both the scala vestibuli and the scala tympani contain perilymph. So here's the vestibular duct or the scala vestibuli. Here's a tympanic duct or the scala tympani. These two ducts contain perilymph. Here is the osseous labyrinth around here. There's the membranous labyrinth that's been pushed to the side. And you know that outside of the membranous labyrinth, the fluid is called perilymph. And so perilymph's in the vestibular duct and in the tympanic duct. The middle chamber, the scala media or the cochlear duct, that's inside of the membranous labyrinth, is bounded by the vestibular membrane on top, named after the scala vestibuli here, or the vestibular duct. So that top membrane is the vestibular membrane. And on the bottom is the basilar membrane. You can see it down here on this lower picture better. There's the basilar membrane. Or if you want to look there, it's there too. So vestibular membrane up here and basilar membrane down there. Now it contains the organ responsible for hearing. This is the organ responsible for hearing right here that's been blown up. And it's called the spiral organ. Because this cochlea spirals, this is called the spiral organ, S-P-I-R-A-L, or organ of Corti. That's an old term. The person's name, Mr. or Miss Corti, discovered that and it got named after him. It says it's comprised of a lawn of hair cells, and check it out, there are the hair cells, okay, which have their hairs embedded in a long gelatinous sheet called the tectorial membrane, T-E-C-T-O-R-I-A-L membrane. That goes all the way down that spiral. So the hairs are in a lawn that goes all the way down, and they're embedded in a tectorial membrane all the way down that spiral organ, all the way to the helicotrema. The hair cells are resting on top of the basilar membrane. There they are, right there. They're resting on top of that basilar membrane. So that's the spiral organ, the organ of hearing. So let's look at this picture again. The stapes, well, let's back up. The ear is capturing sound, channeling the sound into the external auditory canal, causing the tympanic membrane to vibrate, which is transferred to the malleus, to the incus, to the stapes. So the stapes is sending pressure waves into the perilymph of the scala vestibuli, or the vestibular duct. Some of the pressure waves are passing from the scala vestibuli through the scala media, follow the arrows, into the scala tympani. The result is that the scale of media is oscillating with the pitch of the pressure waves. The highest frequency waves are going to cause bouncing up closest to the stapes, and lower sound waves are going to be longer wavelengths, are going to be down further toward the helicotrema. So it's like a piano keyboard backwards. High-pitched sounds here, low-pitched sounds further down. Now, you know, frequency is a sine wave, and according to what the sine wave is, it's going to cause this to bounce, because these sound waves are being sent in by that real fast vibrating stapes, and when it bounces, the hairs that are here are on that membrane right here. The hairs are this whole membranous labyrinth is going to bounce, and when it does that, it pulls on the hairs that are embedded in this tectoral membrane. When the hairs are pulled according to where the bouncing occurs, high pitch up here, they bounce in high frequency, lower pitch, lower sounds. Depending on where this membranous labyrinth is bouncing, that determines what sounds you hear. So it results in the scale of media oscillating with the pitch of the pressure waves. Highest frequency waves are interpreted closest to the stapes. Lower frequencies are interpreted toward the end of the cochlea, further down bouncing. Now, I have distinguished between conduction deafness and nerve deafness. Conduction has to do with the conduction pathway. Your tympanic membrane is conducting sound waves, it's vibrating. Your malleus, incus, and stapes are transferring those vibrations to your inner ear. So that's your conduction components there, tympanic membrane, malleus, incus, and stapes. If any of those is damaged, it's going to reduce or prevent you being able to hear, because sound waves can't be transferred from the outside to your inner ear. So those are the parts of the conduction pathway. Nerve deafness has to do with the, let's look back over here. These hairs have fibers that form the cochlear branch of the vestibulocochlear nerve, which is responsible for hearing. And those impulses of these hairs that are triggered from sound waves are going to go to your brain by way of the cochlear branch of the vestibulocochlear nerve to be interpreted as sound. And your ears are very highly tuned. Sound waves arriving in one side versus the other, that short fraction of a second delay can tell you where that object that you heard is located in your environment. Now I'm going to have you look at nystagmus. It has to do with the movement of the eyes, okay? So this is your first lecture on the general senses.